Welcome to Cosmic Showcase, the channel where we shatter your perception of the universe as you know it. Prepare to embark on a mind-bending journey through the cosmos as we delve deep into the mysteries and uncharted territories of the universe. In this cosmic voyage, we'll explore the astounding, the enigmatic, and the downright mind-boggling aspects of space and time that challenge the very foundations of our understanding. Let's start this mind-bending journey. Have you, like me, ever looked out your window and wondered why the universe was the way it was? As you watched clouds float by or stars twinkle in the night sky, did you stop to consider why we live in a universe that looks quite the way it does? All great truths are simple in final analysis and easily understood. If they are not great truths. So said Napoleon Hill in his book, The Law of Success. And when it comes to the universe, I believe that he is right. There have been many complicated mathematical formulas over the years that have attempted to map out the universe. But when great breakthroughs have happened, and our understanding of the universe has been advanced, it has often been through equations and explanations that are incredibly simple. F equals ma. E equals mc squared. These are succinct enough to be explained in just a few lines of text or a few algebraic characters. But more than just the clouds, what are the great truths that underpin the universe itself? What is time? Why does the universe look the way it does, constantly expanding in all directions, from everywhere? Why does light have a speed limit? And if you have ever wondered these same sorts of questions, perhaps the models in this video that I've developed with my brother might help explain the answers. Ultimately, a great truth must be simple. The ideas here likely still need development. But I believe that they explain the subject in a simple enough manner that they might just be the starting point we need to find the truth. To begin with, let's start with a fundamental question. What is time? On this channel, we've talked a lot about time. As black holes warp space around them, we've learned that time slows down. We've discovered the time-influencing effects of gravity, and even how the James Webb Telescope can peer through time to the distant past, by taking advantage of the fixed speed of light. This all may make sense so far, but what actually is time? You can't taste it, touch it, or feel it, yet time has an unstoppable influence on us, and is pushing us forward whether we like it or not. Doesn't something that impacts everything we do deserve some additional understanding? Thanks to this first model, we are going to have a possible explanation for why time slows down as velocity increases, and why shapes warp when undergoing velocities close to the speed of light. This model is based on recognized scientific theory, where we have taken scientific concepts and combined them into something you may not have seen before. But before we get to that, we have to begin with one foundational idea. Time is actually another dimension. Now, before you double-check that you haven't logged on to some sci-fi channel by mistake, let's discuss what I mean by dimensions. While in popular culture, different dimensions are often described as parallel worlds that are very similar to ours, yet subtly different, in this context, when we talk of different dimensions, we are referring to the dimensions of space, as in three-dimensional space, or 3D space, which may be far more familiar to you. This is by no means trivial though. 3D space is all around you. It is the around you, and is very relevant to our topic. Let's begin by making sure we understand the 3Ds and the relationships between them before we add a fourth D. Broadly speaking, 3D or three-dimensional space simply refers to space that can be measured in three different perpendicular directions. The perpendicular nature of these dimensions is important, but we'll get to that later. Three-dimensional space is usually described as having height, width, and depth, and they all have 90 degrees angles between them. Simply put, objects like us that exist in 3D space can move left and right, up and down, and forwards and backwards. Here we might need something that looks like this, except with little 90 degrees markers between them. Maybe have a little ball moving around in this space. We are comfortable with this kind of space. Using this as our basis, it becomes much easier to imagine what we mean by 2D space, and even 1D space. To move from one space to another, all we need to do is remove or add an extra dimension of measurement or movement that must be at a 90 degrees angle from all previously existing angles. So 2D objects can move in a plane that's bounded by the x and y directions, or the x and directions, or the y and directions, but not all three at once. 1D objects can only move either along x or y or z. Imagine a person who lived in such a 1D world. Their whole existence would be found either moving one way or the other. All of reality would exist either to the left or to the right of them, and would appear as a singular dot. They could not move or see in any of the other directions, and probably could not even comprehend such directions as even existing. Photons whizzing by them would only be visible if they entered the singular line that was a 1D person's whole area of existence. Now, adding extra directions of movement is what's needed to move things up from 1D to 2D or 3D, so, in theory, we can predict what we need to do if we were to jump up to 4D. However, here we hit a snag. While it's easy to draw a line that's perfectly perpendicular to a single other line, or to draw another line on top of both of those lines that is perpendicular to the two previous lines, how would we draw a fourth line that's perpendicular to all three? Surely such a thing is impossible. Well, within 3D space, such a thing is impossible. The best we can do is draw approximations. For instance, it's possible to draw an approximation of a 3D shape on 2D paper by doing something like this. These lines are all two-dimensional, but we look at this and our brain recognizes that this is a picture of a 3D shape. So in the same way, we can probably do something similar to guess what a 4D object might look like using just 3D lines. Mathematicians have attempted to do this, although their results tend to be a little confusing. Although this is mathematically sound as a basis for a 4D object, I personally don't find my understanding of 4D space deepened by looking at it. So, I won't focus on it in this video. There is some evidence, however, that a fourth direction exists, and that we are moving through it right now. That fourth direction, or dimension, is time. Einstein predicted this connection when he linked space and time into one unified space-time in his theories of relativity. According to him, time and space are two parts of the same thing. To me, this connects with 4D space very nicely. Just as there is no real difference between this direction and the x or y directions, so too would there not be any difference between time and space if time is just another direction, albeit one that we can't see. And time is important. Without time, our 3D space wouldn't move. It would perpetually be in one state, because it's time that allows us to move about in it. But why can't we see it? Why can't we look in the direction of time? To explain this, let's look at the difference between the different dimensional spaces. We best notice this when we consider what 2D objects might look like if they were to move around in 3D space. This is where we start to delve into the model. Let's begin by visualizing a standard 3D space. But because we want to eventually see all of space and time in one model, let's cheat a little. Let's compress all of 3D reality as we know it into a flat two-dimensional place. In this plane, let's make that our XY plane, which we will label space, which frees up this dimension for time. In this model, all 3D people are now just 2D. A 2D person could exist and live their lives in the place marked space at the bottom of our chart. However, by moving them up on the chart at a constant rate, they also are moving through time. Let's, for ease and convenience, say that the top of our diagram is the future, while the bottom is the past. So the higher up our 2D person goes in this diagram, the older they get. As we don't seem to have a whole lot of control over our ability to travel through time, let's imagine for a second that our 2D person travels upwards at a constant rate, as if there is some consistent force or wind at play pushing him upwards towards the future. Sadly, we cannot slow down time for ourselves simply through willpower, no matter how much we might want to do so. However, it is misleading to say that we can't change it at all. The faster we travel in space, the slower we travel in time. This is one of the guiding principles of Einstein's relativity. This model can express this idea through the power of vectors. As our two person tries to move to their left or their right, their vector of travel changes. While traveling at a fixed rate, like a sail on a ship catching a breeze, we can only go as fast as the wind takes us, so the vector coming out from their front must always remain the same. To travel the fastest through time, our 2D person must orient his vector completely in the future direction or upwards. However, if they are to travel any amount in either direction to their sides, they can only do so by pointing their vector away from their direction of travel. They have motion in the x direction now, but they have done so by reducing their motion in this direction. They are moving through space, but at the cost of moving a little slower through time. Taking this to its furthest extreme, our individual has fit completely on their side and now only has motion in the direction of x and none in the direction of z. They have velocity in space, but not time. So I suppose this implies our vector is the speed of causality or the speed of light. If this is the speed we're talking about, then moving at low speeds through space would not have any noticeable difference in our speed through time. We'd have to go really fast before we started to notice anything. The vector still mostly points upwards. An interesting result of this model is that, from the 2D man's perspective, nothing has really changed. He has his own view of what reality is. For him, the vector coming out of his chest is still time. The dimensions of the plane he's lying flat on is his space. To him, it's the rest of the universe that's gone a little weird. But he himself is perfectly normal. However, once he reorients himself, it is clear that the rest of the universe has moved on without him. This is clearer if we introduce a second 2D person. Initially, both of our individuals do not move in space. All of their vector is pointing in the direction of time. Nothing that strange seems to happen so far. However, if our stickman on the right turns and vectors at near the speed of light for a bit and then reorients himself, while the 2D man on the left just stays where he is, it becomes clear that our 2D men have not moved at the same rate through time. Assuming that our two stickmen can still somehow see each other, let's imagine that they somehow project an image of themselves onto the other's space plane. They'd immediately notice that there is a difference in age. The one who traveled at the speed of light did not advance so quickly through time as the other who remained stationary, and so is younger. But why do we find this model so compelling? Well, it is because of what those projections would look like during changes in direction. From the point of view of the first stickman, initially, the projection of their friends seemed to be fairly normal. However, as they started traveling very quickly in space, and their vector oriented in a direction away from time, a 2D shape reveals its inherent flatness. From a face-on perspective, it goes from this to this. The speedily traveling stickman appears to flatten, with an effect that's more pronounced the faster they go, with the flattening taking place in the direction of their travel. The stickman who remains stationary might wonder at the strange change that is occurring to their friend, never comprehending that it represents a reorientation of a 2D figure in 3D space. Now, what captures my imagination about this is that this same thing happens in real life. According to Einstein's theories of relativity, objects traveling at great speeds in 3D space would appear from an external observer to flatten in the direction of their travel. This squishing effect happens exactly in line with this model, and is to do with time dilation. However, from the person who's traveling's perspective, they do not flatten, but it is the rest of the universe that warps. From their perspective, everything would stretch at the edges of their vision, while their destination would seem further away, which is again what this model would predict. The only difference is that in this model we're just exploring a 2D object stretching, so the stretch is in only one direction, while in real life it's 3D, which means it stretches in two directions instead. But that is what you might expect as you turn away from our conventional 3 dimensions and start orienting yourself away from time. But if this is correct, so what? Why does this matter? If time is truly a direction, then it deepens our understanding of the universe. It also raises more questions. What is the force that pushes us ever forward in time? Why does it seem that we can never move against it? Although in this model, there is no reason why a vector could not point downwards, in real life, this doesn't seem to ever happen. This model also answers the question of, if time is a direction, what is our shape in time? Does part of us protrude into the past or into the future? According to this model, that does not happen. We are flat pancakes in the fourth dimension, pennies that look round when you look at us head-on, but revealing our thinness when we turn away from you. That's a strange thought, but may just be true. This might explain why we are unable to see through time. We just don't extend enough in that direction for it to be visible. Your form might be quite different than you at first thought. It's useful to consider the existence of other dimensions beyond the three that we see, but there are other edges and frontiers in the universe that pose further questions. For one, does space ever end? Is the universe inescapable? If we were to conquer the limitations of light speed and were to travel to space's furthest edge, what might we find? Just more space, infinite planets and planetary systems. Or would we somehow come back to where we started? Amazingly, according to scientists, all of these are possible, but which one is correct comes down to the nature of that unseen world all around us. We need to understand the shape of space, and to do that, we need to begin by talking about infinity. You likely are already familiar with infinity. In maths, it is the concept of a number so large, it cannot possibly be beaten. Of course, no such number exists. For any number you can name, I could come up with a number that is at least one larger than it. But in a way, that's sort of the point. In infinity, there is always another number. And when it comes to our universe, we have so far discovered no edges. There may always be another star or planet. An infinite universe is a little mind-boggling for us. We live in a very finite world, with edges and endings. So the idea that there might be literally infinite more planets out there is a little bewildering. However, as we develop more and more powerful telescopes and push back the darkness further and further at the edges of what we can observe in our universe, all we are finding is that even the darkest patches of the night sky are turning out to be brimming with stars. So increasingly, an infinite universe might be something we are forced to contemplate. But that is not to say that just because the universe is infinite, there are not a finite number of things in it. That may sound a little counterintuitive, but let me show you what I mean. Believe it or not, there are different kinds of infinity when it comes to our universe. 3 possible scenarios could be true: a flat universe, a spherical one, or a hyperbolic universe. Allow me to explain. In a flat universe, if we were to form a grid to broadly represent reality, everything would seem fairly standard. All the lines would either be parallel to each other or perpendicular. An infinite universe of this variety would simply extend outwards in all directions forever and ever. This is a little boring, so I won't spend too much time on it. However, this is a lot like what we perceive the universe to be. For the most part, all lines of direction appear straight to us. We can distinctly see the planets and stars around us, and we notice no real curving or warping. However, this is not the only way that the lines can be drawn. Consider for a moment a black hole. You may immediately notice the strange rings that appear to run around its equator, as well as across the top of it and along the bottom. This is something of an illusion. There are no rings across the top or bottom of this black hole. What you are seeing is the equatorial ring that's on the other side of the black hole. However, due to the powerful gravity of the black hole, the light that is hitting it is not bouncing off upwards or downwards into space. Instead, the rays are curving towards us as the black hole's gravity pulls them in. You are seeing the top and the bottom of that ring at the same time. Light being bent by gravity. What do I mean by that? Actually, This is an excellent example of our second kind of universe. In a flat universe, all the lines that make up reality are fairly straight. But what if we were to come up with a rule? All the lines must instead curve towards each other. There is only one way such a universe could be drawn, and that is in a sphere. Consider trying to draw two parallel lines on a sphere. You might start off well, but would quickly realize that your task is impossible. All lines would converge towards each other, intersecting at least twice, as they return back to where they started. What would a universe that was based on these kinds of lines look like? Essentially, rather than going in the straight line you thought you were going in, you actually would be traveling in a massive curve. It's a little bit like those computer games where you travel off one end of the screen only to reappear from the other side. In a spherical universe, you could try to travel infinitely, but ultimately, you would only end up arriving back to where you started. With a powerful enough telescope, and if light were to travel a whole lot faster all of a sudden, it would be possible to look at the back of your own head. This kind of universe contains a finite amount of things, but it appears infinite just because you keep bumping into the same things infinite times. Thanks to objects like black holes and powerful stars, we do indeed have evidence that our reality sometimes is a curved, spherical one, at least near large bodies of mass. The inside of a black hole's event horizon is this kind of infinite space. No matter what path you take, you can never get out of it. However, let's consider our last example, the hyperbolic universe. This one is the hardest to visualize, but the idea is simple. Instead of having all lines remain parallel or move towards each other, every line must move away from everything. Drawing this is inherently tricky because everything keeps getting wider exponentially. The only way you can do that is to either buckle your nice flat disk until it becomes something like this, or warp what you are seeing like this. All of the objects in this image are squares. However, they are squares that are obeying our rule that all their lines must be diverging away from each other. This leads to the very strange situation where you can have 5 squares all meeting up at a corner, instead of the usual 3 that is possible in normal 2D space. Alright, this seems a little confusing. What does it mean if space is hyperbolic? Well, let's consider what it is we are curving around. You might have noticed when we talked about our spherical shape that there must be something we were curving around. That direction of curvature is in regards to time. Imagine, if you will, a series of timelines. Just remember for this model that objects in time move forward along their timelines in the direction of up or the future. If they move left or right, they are moving through space, getting closer to each other. If we introduce a large mass into this model, it warps the timelines. Now, if you were a small object traveling along one of those arrows that got too close to the mass, suddenly your path of travel no longer goes directly up towards the future, it pulls you left or right towards the mass. There are reasons for this, but the essential thing to recognize here is that now, your straight path towards the future pulls you in towards the planet, so you'll have to accelerate away from it just to stay on a straight path. In a nutshell, you are experiencing gravitational pull. Even the planet is affected by this. The atoms on either side of it are squeezed towards the center of mass, as if it were being forced down a narrow tube by giant, invisible hands. Let's get back to hyperbolic space. In this model, the opposite thing is happening. All lines are moving away from each other. We could represent this by curving space and letting our timelines be straight, which is nice because it captures the idea that from your perspective, your time is always ticking forward normally. But let's warp this slightly so that it's space that is flat. It's all a matter of perspective. After all, here, parallel lines are also impossible. But this time, rather than converging, all parallel lines diverge more and more. Everything moves further and further apart. Why does that sound familiar? It is because that is what the universe is doing. This is not noticeable within a galaxy, where there is enough mass and gravity to keep everything together. However, from what we can see of the universe as a whole, every galaxy is moving away from every other galaxy. Scientists try to explain that with dark energy. But maybe all that is happening is that the universe is just naturally hyperbolic in its shape. So what would that mean if the universe really was hyperbolic? Well, for starters, it would mean that the universe was really infinite. The flat space we looked at was infinite. For each light year you traveled out, you discover another light year's worth of space. However, with hyperbolic space, you discover more than another light year's worth of space. It's like opening infinite doors, except inside each door are two new ones. The possibilities would be far more endless, far more infinite, than in just regular flat space models. But also it means that given enough time, the rest of the universe would drift away from us until our galaxy was all that was left. Scientists have looked out across the universe, however, and have not noticed this hyperbolic space in action. In fact, things all look pretty flat. So perhaps flat space is the correct answer. Yet, this still leaves room to me for hyperbolic space to be the default. After all, if matter is curving space towards it, and the universe appears flat, it would make sense that the universe was curved in the inverse, at least to some degree. Perhaps all three models are true. Perhaps the universe is by default hyperbolic, but mass brings it together in such a way that it perfectly offsets the inverse curves of the universe to the point where everything appears flat. There certainly seems to be some evidence that this is the case. But it's very difficult to know for sure. Which model do you think is correct? Or maybe you feel that we do not live in an infinite universe at all. Please leave a comment down below to tell me what you think. But for now, just remember, the unseen world might be a lot more influential on our universe than we are currently aware of. Thank you for joining us on this mind-expanding journey through the cosmos. If you've enjoyed challenging your perspective on the universe, don't forget to like, share, and subscribe to Cosmic Showcase. Keep exploring, keep questioning, and remember, the cosmos is full of surprises waiting to be uncovered. Until next time, stay curious.